last question is my favorite. So we're going to be proving a big O question here. So again, I'm going to draw a line in the middle. Just, let's do a straighter line. Just so that, you know, we have enough room. Alright, so this is going to be a theorem proof. So let's write out what exactly they want. And I find even if they, for whatever reason, the profs decide not to write it in predicate logic, I write it in predicate logic because the predicate logic itself like tells me exactly what I need to do. It's almost like an instruction once you're used to it enough. Okay, so we have this part and then now this part. So G1 O F1 and G2 O F2, then G1 plus G2 O, running out of room there, F1 plus F2. Okay, so let's do this. Okay, so first part, let's take care of this. Let F1, F2, G1, G2 be functions from natural number to positive, to a real number that's 0 or positive. And let's assume, okay, so this is the important part here. So once you write the assumption, you want to write out exactly what this means if you're not familiar with it. And I know I'm not familiar with it enough, so I always do this. So notice here I have the kind of like I put 1 there because I know there's going to be more than one of these and I don't want to get them mixed up. So let's let and 1, then okay, so this is G1 smaller than or equal to C1 times F1. Okay, and then we assume this. And 2, G2 smaller than or equal to C2 times F2. Okay, and we want to show this. Let's see what we want to show here. We want to show this. So I show G1 plus G2 is in the, oh, we should do an O there, big O of F1 plus F2, i.e., then we'll just do a new line here because this one's going to be a little bit longer, C3, N3, of every natural number, n is larger than or equal to 3, and we have G1 plus G2 smaller than or equal to C3 F1 plus F2. Perfect. Okay, so first of all, we want to unlock these two statements, and we can't do that unless this and this is true. And for this one here, we're going to need to choose C3 and N3. So let C3, let N3. Okay, and we're going to choose N3 to be N1, N2, whichever one is larger. So you can kind of choose what you do. I sometimes write the max, sometimes I just add them together. Okay, and then C3 this, then N3. Okay, perfect. Alright, so next step is this. Oh wait, okay. So because of this assumption, we know we unlocked these two things because we satisfied it. But first, we have to let n be an arbitrary So then all these are satisfied. So we know that these values exist, right? We just don't know what exactly those values are. So we know that G1 smaller than or equal to C1 times F. And before we did all this, we don't have access to it. That statement is saying that if these values exist, and if n is if n is larger than n2 and larger than n1, then this is true, right? So actually the proper step here is we write let n be a natural number, and then we assume that n is larger than or equal to n3. And because n3 is a combination of n1 and n2, you know that these are satisfied, right? Okay, so now we can use these. Okay, so we take a look and we go, this is what we want. We can add these, each side to each. So we write add together. Then we have G1 plus G2 smaller than or equal to C1 times F1 plus C2 times F2. All right. Okay, that's good. So, but we want to somehow, get the C3 out here. So let's see here. Well, we can go like this. Maybe this will be a little bit more clear. C1 plus C2, F1 plus C1 plus C2, F2. And this is true because we know that C1 and C2 are, they're positive. What are they again? Let me check. They're positive real numbers, so they're going to be larger than 0. So adding them together is obviously going to be larger, right? So then we know that this part here equals C1 plus C2, F1 plus F2. There we go. So now this is what we said is C3, which is equal to C3, F1 plus F2. And that's it. That's the whole test, and I hope it was helpful.